this conference. It's a long time since I've given a chalkboard talk, so we'll see if I can get back the hang of it. So I'm talking about parabolic Hilbert schemes and rational Cherednik algebras. It's all joint with Eugene Gorsky and José Cimental, who's here. And all right, and rational Cherednik algebra, I'll be abbreviating that RCA. So let me start with the theorem and then explain the parts of it. So with Eugene and Jose. So I'm going to start with C, a plane curve singularity. Let's see if I can get. Oh, there's one light. Okay. So hopefully I'll be able to juggle these colors well. So M and N are two relatively prime integers, positive, and I'm taking this plane curve singularity, x to the m is y to the n. And sort of the first statement is a rational Cherednik algebra that has parameters depending on M and N acts on the equivariant cohomology of the parabolic Hilbert scheme, which I'll say what that is eventually, on this curve. And not only that, as a rational Cherednik algebra module, it's isomorphic to a particular irreducible module we'll call L of Triv. So in other words, we're giving a geometric construction of a representation of this algebra. Part B is that the spherical rational Cherednik algebra, and I'll explain what I mean by spherical in a bit, acts on, again, equivariant cohomology, but then just the plain old Hilbert scheme without the parabolic, and isomorphic to I'll say E of L triv. So I'll say now it's spherical. So E is the trivial idempotent in the symmetric group. The symmetric group is the group algebra, the symmetric group is a subalgebra inside my RCA. So you have a trivial idempotent. And if you take the corner ring, you put trivial idempotents on either side. That's what I mean by spherical. So if you take a representation of the RCA and you stick an E out front of it, it becomes a representation for the spherical. Okay. And there's a part C, which I'll just put up here, but not have time to actually talk about it all. But there's something called a quantized Giesecke variety, which acts on, again, equivariant homology of something I'll call the compositional parabolic Hilbert scheme, which has an extra parameter R in there. And then what you get is isomorphic to a particular known representation of that has this extra parameter R. So again, I'm not going to talk about that at all or define it, but I thought it's also a nice part of the theory. If you know anything about Giesecke varieties, and Jose is totally the expert on that. So you can talk to him about that if you want to follow up on that. Okay. Yeah.
What is this notation? You take homology.
Oh, I'm taking this. So there's a torus action. I'm taking equivariant homology. In all cases, I'm doing equivariant. Yeah.
The same side and both. Okay.
Yeah. Sorry. Oh, bad handwriting. Yeah. Okay. So let me, before defining these algebras and what I mean, and reminding you about Hilbert schemes and what I mean by parabolic, let me first contextualize this theorem, or rather recast it in the language of some of the things we heard in the talks yesterday. Okay, so on the left-hand side, I all have these three different algebras. I could just say instead quantized Coulomb branch algebra. Okay, and then acts on homology of instead a generalized affine Springer fiber. Okay, and not fill in the and it's isomorphic to some known thing. Okay, so as we heard, so from work of Webster, well, I guess I should start out with, right, so we know BFN had Coulomb branch algebras, and Webster made our quantized Coulomb branch algebras. The fact that these Hilbert schemes and parabolic Hilbert schemes can be realized as generalized affine Springer fibers, I would say we should look at work of Garner and Kivinen. Okay, and the fact that we have these quantized Coulomb branch algebras acting on these generalized affine Springer fibers, we can look to work of Hilbert, Kamnitzer, Weeks. Oops, sorry for my handwriting there. Okay, and then also the fact that when you do this, translate into both of these sides, and then you say this action is the same action you would get from here, that would be looking at LePage-Webster. Okay, and possibly I have left out some citation and attribution of people's work that goes into that. Feel free to say if I'm missing you. Yeah.
Is recasting part A or part B or both?
This A, B, and C. A, B, and C. Yep. Can all be recast in that way.
Ben did a lot of stuff, but the quantized Coulomb branch algebras are already defined in BFN.
Ah, okay. Oops, sorry. I thought it was, I've done that. Okay, thanks. All right, so maybe I meant more on getting at the action. Okay.
Should also be citing like Nakajima.
Yes. Nakajima and
Yeah,
okay. Yeah.
Coulomb branch algebras too that are.
BFN defined on Coulomb branch.
So is that with Nakajima and who else you said? Oh, well, we have Nakajima in the BFN, so I'll leave that there. But yes, no, thank you.
Oh, it's Kodera?
Oh, Kodera. Kodera. Okay. I might misspell you, Kodera. Sorry about that.
No.
Oh, there's no I.
I mean, no, E instead of an AI.
Oh, Kodera. Okay, Kodera. Sorry about that. Okay. So, and then I should also say another way to get at A and B, you could take an approach. Let's see here. You could look at a Blumka of Eugene and other work of Eugene that looks at actually the trigonometric Cherednik algebra, of which the rational Cherednik algebra is like you can think of it as degeneration, and they have a geometric construction of the corresponding modules there. But to pass from trigonometric to rational there, you have to have a complicated filtration and take the associated graded there, and that's using a lot more intense machinery, and our proof is kind of more straightforward, elementary. And of course, if we're talking about RCA type things acting on homology of Springer fibers without the generalized, you should also certainly look at work of Lustig and Varignola-Vassereau. Okay, so this is what I'm talking about, not at all in the language here. I'm going to be much more with the algebra and combinatorics. Okay. So I'm already behind schedule. Okay, so all right, so let's start talking about what these algebras are. And so let me just remind you that if we just have the symmetric group Sn, you can get, you can construct the irreducibles geometrically, again, by taking, well, homology or cohomology of, some space like, flag variety. And, like the SIs, you do some forgetting a flag, pushing, pulling correspondences, and so on. On the other hand, you don't have to do it geometrically. You can do it combinatorially, which is how I always learned to do it. And when you do it combinatorially, what do? Your irreducible representations are parameterized by partitions of n, right? Tuples of positive integers that add up to n. And your bases of your modules are given by standard tableau. of shape lambda, if lambda is a partition. And another ingredient I like to throw in there is that you might have Jusis-Murphy operators, and they act with nice spectrum that is governed by the diagonals. So what do I mean by that? We might take a partition like n, which means I'll have one row with n boxes. Let me just stick to n equals 3 today, because that's all I'm doing, right? So what's a standard tableau? You fill it with the numbers 1 through n, increasing across rows and down columns. I only have this one row. There's only one standard tableau. And if you wanted to know, there's a first and a second and a third Jusis-Murphy operator. These are some commuting operators in the group algebra. And if you want to know how they act, you look at the diagonals and you have various labels on the diagonals. For instance, standardly, we label them 0, 1, and 2. And so the first Jusis-Murphy operator, I look at where the box 1 is, it's on the 0 diagonal, and that's telling me the eigenvalue that goes with this eigenvector that goes with the standard tableau. Okay, and so that's how I like to approach representation theory. And we could notice, so I'm building my way up to RCA eventually. We could enlarge a symmetric group, or the group algebra, the symmetric group, by throwing in a polynomial algebra and having the SNs permute them. So it's like a semi-direct product, or really I'll say a smash product here. And you can inflate up such a representation by having all the yi's act as 0. Okay, and that's a little bit boring. Note that all the yi's are conjugate to each other by conjugating by an SI. So the sort of the spectrum that you get is, I'm going to say, is boring. The Jusis-Murphy operators give you much more information about such kinds of representations. Okay, and notice that I'm not taking Laurent polynomials, I'm just taking polynomials. So this is not quite the group algebra for Sn Reith Z. I would have to have y's and y inverses if it was that. Okay. All right, so now the rational Cherednik algebra that I'm talking about, people often put in, well, we'll say HTC attached to the symmetric group. I'm just being type A today. And I'm taking the nth dimensional representation of the symmetric group as part of my input data. And so many people will instead put in the n-1 dimensional irreducible representation, the so-called reflection representation of Sn here, and study that rational Cherednik algebra. I'm not doing that. This makes the combinatorics better. It's kind of like working with GL versus SL. Okay. And as a vector space, this is isomorphic to take polynomials in X's, take your group algebra, your symmetric group, and take your polynomials in Y's. Okay. And the symmetric group in the Y's, they just act on them like the smash product. Same with the symmetric group in the X's. Y's commute with each other, X's commute with each other. The commutation relations between Y's and X's are more complicated. I'm not even going to write them down. Okay, they're just there. It's not actually important.
Sorry. This thing where the camera follows you around sort of stopped working. Can you just like walk over there and see?
Uh-oh, it stopped following me. Great time to have a water break, or any other questions.
The only thing I changed was this thing.
Yeah, I think that when PD is
Oh, it's because we had, okay, you can turn the screen thingy back on.
Back on. Now is it telling you again?
Oh, wait.
No, is it TV back on? TV's back on.
I broke it. Oh, well. I'll try to favor these boards a little more. How about? Well, no, I lied. Maybe not. Okay. All right. Okay. So we take HTC and some element in our field, like so I'm working on the complex numbers, I can rescale. I didn't define this algebra, but it has these two parameters T and C that are in the relations. They're in the relations for how X's and Y's interact, basically. And they're homogeneous in a way that you can just rescale them both and get the same algebra, just rescale your generators. And so most people then will just set the T to 1 and do H1C and say there's only really one parameter called C. Or there's also the case where, T is 0, and then you could have sort of H01. So kind of like projective space, yeah. And so I am going to care about, when I talk about this theorem, this C is going to be my M over N. Right. Or if you want to undo this scaling, instead of saying H1C with C being N over N, we could then instead do H, and I have to, that means I'll have an N there and an M there. You could also do that. Okay. So if you're okay with fractions, deal with H1C. If not, deal here, but then you can get N and M really mixed up with each other. Okay. So, so that's the rational Cherednik algebra I'm taking up to not telling you what it exactly is. And so it has a standard module, I'll call it delta triv. And what is that? You take your symmetric group and the y's, this part. You take your trivial representation, that's this guy here. Oops, I should have called this is guy where it's just one row, that's called triv. And also, I should say, triv is cut out by our idempotent E that defines our spherical Cherednik algebra. So you inflate that up, and then you induce up to the RCA. Now, if you believe me about as a vector space, that means that as a vector space, this is just isomorphic to polynomials. And so people often call this the polynomial representation of the Cherednik algebra. If I told you how all the operators acted on it, it turns out it's a faithful representation. So that would give you a very concrete way of knowing what this algebra is. Okay. And so this has a unique simple quotient that we call L of triv. That is the representation that occurs in the parts A and B of the theorem that we're going to construct geometrically.
How big is it?
How big is it? That's a good question. So because I am doing the kind of GLN versus SLN version, it will always be infinite dimensional. Okay. If I would put the reflection representation here, and M and N are relatively prime, its dimension then would be finite dimensional and would be a generalized Catalan number given by N and M. In other words, it would be counted. Oh, no, sorry. Not this. The Catalan number would, come from this. It would be M to the N minus 1 if it were working with SLN versus GLN. So, but it's sort of M to the N minus 1, and then you kind of have like an infinite cover of that by being able to have positive degree. So for instance, if we took a smaller representation here, we'd have to add relations like the sum of the x's is 0 and the sum of the y's is 0. And then you would see that the sum of the x's is some extra thing in here that you can like add on to everything and like up the degree. And but if you smash that down, if you kind of mod it out by the sum of the x's, the dimension of this would be M to the N minus 1. But we're infinite dimensional here. But these are the things that come in with all the Catalan combinatorics and parking functions. So, all right, great. Okay, so now this representation is just polynomials. Let's see, I think I can erase. I'll erase this board first. So polynomials, great. You have a basis of monomials, or least any basis will be then indexed by whatever indexes monomials, and those are just given by the exponents. So right, so I've got my right. So your basis corresponds to if I have x1 to the a1, xn to the an, we can just take this tuples a1 up through an. The ai's are exponents, so they're non-negative integers because I'm not in this Laurent polynomial phase. And then you could ask about, and this also somewhat answers Vera's question, is how big is the quotient? How big is this basis? And I should say, I can say this explicitly for C equals m over n. It's known for other kinds of C's too. If C is generic, these guys will be the same. The polynomial representation will be irreducible, but for m over n, it's not. And so this basis, I'm going to index it by something I'm going to call script a m over n. And so what is that? Those are going to be my n tuples such that the difference between any two is less than or equal to my m. And further, if the distance is exactly m, then ai has to come before aj. So let's do some examples. And I should say this, we should say Stephen Griffith maybe worked out these combinatorics and cutting out how big L is. All right. So let's take n is 3, m is 4. All right. And so, all right, dispense with my colors for a little bit. So for instance, what are some things? So like 0, 0, 0 is always going to be good. Okay, 4. So if we look at 4, 0, 0 versus 0, 4, 0. Okay, 4, 0, 0 is okay. The distance between these is 4, but the 4 comes first. 0, 4, 0 is not. Okay, because there's the 0 above the 4. On the other hand, something like, right, 5, 7, 3, that's okay. Okay. So, all right. Now, I said that when I look at the representation theory of, say, the symmetric group and related algebras, I like to do it combinatorially. And so if it was a symmetric group, I would have tableau and partitions and so on. And you can do that. You can make a nice model of this representation if you use basically periodic tableau. Okay, so let's make our tableau model of L triv again at these parameters m over n with m and n relatively prime, but you could do this with other parameters a little more carefully. So let's just pick one of these 5, 7, 3 that indexes something in my basis, and let me spit out a standard tableau. Okay, what standard tableau is it going to be? Well, I say, okay, I have the 1, 2, 3 position, and I need to use my 5, 7, 3 data. And let me just multiply everything in sight by my n, which is 3, and add. And in this way, I'll get 16, 23, and 12. And it's these numbers that I sort to make it standard, and I stick them in a tableau. Okay. So by this process, what are my tableau going to be filled with? They'll always be filled with integers that are distinct mod 3 and increasing. Okay. And positive because my AIs are non-negative. Okay. So that gives you another answer of how big this module is. You have all standard tableau like so. Okay. And because you're filling them with numbers.
Just one row.
Yeah, so as of now, it looks like it's just one row. I should say they're kind of periodic, or they're sort of semi-infinite periodic. And so, yeah, so let me show you what's missing. So this is like, it's a periodic tableau because I have this kind of mod 3 condition. So I'm like, where are all the other integers? Shouldn't I see all the, like, you know, here I had to fill with like 1 through n. We really could think of this as some infinite tableau that's filled with all positive numbers, okay? But it's enough to give a fundamental domain because there's some periodicity that's happening from this mod 3. And so let me show you what happens and how we make things periodic. So if we had 0, 4, 0, which is a bad guy, right? That's a bad guy. What would that spit out? That would spit out 1, 14, and 3. And you would say, hey, I do 1, 3, 14. Like, what's wrong with that? It still looks standard to me. It's the periodicity now where we're going to see what happens, which is when you move over n boxes, you want to add mn to everything, which in this case is 12. So you've put, you know, 24, 30, 35. Okay. Oh, thank you.
That's a,
Yeah, and if you do it right, the gap from here to here is 4, the gap from here to here is 7, and so this should also be a 4 and a 7. But then this periodicity, you're like, okay, you didn't know yet that this gap would be 1. If you try to do the same thing here, 1 plus 12 is 13, and you're like, oh, 13. The same way that that's not standard is the same reason why this was not in my indexing set. Okay, that's your periodicity condition. And you could just imagine that this strip goes on doing this 12 periodicity, certainly infinitely out in this direction. At some point, it stops here when you start hitting negative numbers. Okay. But it's enough to just give the fundamental domain and then just check, or maybe fundamental domain plus 1 more box. And I should say, no, I won't say, but ask me what to do to fix this later, because I don't have time to say here. Okay. All right. Oh, and then I guess the other thing I should just say briefly, and again, I'll say more after the talk in the interest of time. In this combinatorial model, we had Jesus-Murphy operators, and we labeled diagonals, and from that, we kind of knew some extra information. The rational Cherednik algebra has some operators that are not the x's or the y's. They're Dunkl-Opdam operators. They're commutative. They have a nice spectrum. The way you read off and you label the diagonals, we're going to say this is 0. This is actually -4, -8, -12, and so on. I used green because that 4 is from my m, which is 4. And this, 0 to 12, and then I added 12 to that number, that periodicity is baked in. Now you could say, wait a minute, I have something that's, if I'm adding 12, I should see all the numbers. I shouldn't just see numbers, these from these things mod 12. I'm missing a quarter of my numbers. And again, like I said, this is just kind of a fundamental domain for something. There's actually, it turns out there's going to be M4 sheets of these. And so, where are the diagonals? There's another sheet here that'll pick up a -3 diagonal, a -6 diagonal, a -9 diagonal by adding 3 to everything in sight here, or adding 6 or adding 9. In the interest of time, I'm not drawing those, but I'm happy to explain those combinatorics to you later because I really love that stuff. And so, yeah, so for instance, if I wanted to know if I have Dunkl-Opdam operators, which are kind of like my Jesus-Murphys, I want to know how U1, U2, U3 would act. I would have to look at all these 4 different sheets. I would have to find a cell that had a 1 in it and then read off which diagonal it's on. And that would tell me the number here. And I can, for this one, it's like 11, 13, and 17 in some order. It actually ends up being 11, 13, and 9. So you can, if you extend this out, you should find those boxes on those diagonals if you do it right. Okay, so, all right. So now that I've said the algebra side of it, let's go to the geometry side. Yeah. Okay, so back to my plane curve singularity, Hilbert schemes and parabolic Hilbert schemes. Whoops, that's okay. Joel warned me of that. So my curve is y to the n, and their GCD is 1. And so my Hilbert scheme. So first, let me do sort of the punctual Hilbert scheme on this curve. It's the moduli space of ideals in the ring of local ring of functions. I'll say more on that in a second, such that the complex dimension of your quotient ring is this integer k. All right, and for this curve, that means my ring of functions, I'm being local 0. Okay, dropping the colors for the now. So power series in x's and y, modulation x them as y to the n. And notice that you could reparameterize and just say take power series in z to the m and z to the n. Okay, take ideals there. So let me build up to parabolic to get the space we're going to take the homology on to realize this representation here. So first p hilb superscript k n plus k. All right. Again, on this curve. So those are going to be basically flags of ideals. So my function ring containing some ideal, I'll call it ik plus 1, ik plus n. So the subscripts are denoting the codimensions. So this I, which is dim O mod I being k, I could have called it an I sub k. So for instance, this one, codimension k plus 1, and k plus n. And we force that ik plus n should be x times my starting k sub k. All right. And notice then, right, going first to last, the codimension should be n, and that works out well because of this relation here. In other words, an x is like a z to the n. Yeah, and so it's kind of like we're killing a z at each step. All right, and now let's glue these all together, and I'm going to call it p hilb super x to be the union over all k of these parabolic Hilbert schemes, k to n plus k on my curve. Okay, so again, the m, so we could easily swap the roles of m and n in this by swapping x's and y's, right? And instead of multiplying by an x or multiply by a y, but we had to pick one to work with. Okay, all right, and the torus acts by rescaling x and y. Well, you want to do it so that it will be alpha to the right nx, because x like has degree sort of n with respect to z, and alpha to the m y. Okay, so now this is my geometric gadget with respect to which I'm going to take this C star equivariant homology of. So let's consider what this space looks like. Okay, and before we do that, let's notice that you could, if you wanted to, let's see how this color works. You could, if you wanted to, whoops, just pick out ik, that leading ideal from here. If you did that, that would give you a map just to the ordinary scheme. Okay. And so observing that, if you remember, the initial theorem had like a part A, B, C, and A was about rational trending algebra, B was about spherical. Going from to the spherical comes as a corollary by sort of everything you do here, just pick out this I sub k, going from parabolic Hilbert scheme to just a Hilbert scheme. Okay. All right. So, okay. Let's look at this space. Because everything is nice and lovely, a basis for this is indexed by torus fixed points. Okay, so let's look at a basis of this. Let's understand the torus fixed points on our Hilbert scheme. So they're going to be monomial ideals. Well, flags of monomial ideals. Yeah, so we're going to need everything to be monomial ideals. What are ideals going to look like, and how should we think about them? Okay, so let's again keep with n being 3 and m being 4, unless I mixed it up, right? So because x to the m is y to the n, and this 3, we only need to talk about 1 and y squared. Once you have y cubed, that's x to the 4th. So don't worry about that. And how can I think about an ideal? Well, I mean, this is like standard stuff. You just kind of draw some staircasey looking thing here and say, take every monomial above the line. And that gives you a nice ideal, because you have to be closed under multiplication by y in that direction, closed under multiplication by x, which is why you can just trace out a path, kind of staircasey path here, and that describes an ideal. But notice that if an ideal contains some x to the a, y to the n minus 1, that means we're on the top line here. Then it contains x to the a, y to the n, because it's closed under multiplication by n. But y to the n is just x to the m. Yeah, so we automatically get x to the a plus m. So in other words, anytime you have something on this, top line, so if you have x squared, y squared, that means we're going to get x to the 6 is forced to be in there. In other words, when you draw this line that cuts out some kind of ideal, it can't be too thick. It can't be too wide. It can't be wider than 4 apart. Okay, and where have we seen you can't be wider than 4 apart? Right, that's our condition up here. So, all right. And so if we have a, let's go back to our 573. Okay, so 573, that should give me a flag of ideals. And how am I going to do it? Let's see. I'll say here's my 0, 1. Oh, I'm going to do it. I'm going to do it on here because it's a little bit nicer. 0, 1, 2. Let's ignore the blue line. 1, 2, 3, 4, 5, 6, 7. They're identical pictures, yeah. But I thought this one I wanted to kind of leave up for record keeping and draw on this one, and I forgot that. So then at 3, so let's make a cut at 3, a cut at 5, and a cut at 7, and then make that be our shape. Oops, I did it wrong. Okay, wait. There we go. A cut at 3, a cut at 5, and a cut at 7. Okay, so at the moment, that's just one ideal. But 3, 5, and 7 are in some kind of order, and order matters, right? 4, 0, 0 is definitely not the same as 0, 4, 0. And so what I actually want to do is I want to read this 3, 7, 5 from bottom to top, which means that at the next stage, do this. Okay. So I have this, right? So that means at the next step, I want to add, or rather, I want to subtract that monomial out of my ideal, and I want to move my wiggly line over at where the 3 is. Okay. Then at the next step, I want to do the 7. So I'll have, I already have this guy, new wiggly line. Then we add in at the 7. And then finally, we add in at the 5. And then we have a new ideal. And notice, starting from here, and this is our I-18, we said this has to be x times I-15. The very last one you've had x. Yeah, multiplying every single thing by x just slides your contour over by 1. And that's what we've done in the end. So we've ensured this condition. And you can see if we had swapped the 7 and the 3, we would have added this dot first, and we would have gotten too wide, and we would have fallen out of a legal ideal in there. Okay, so now you can see why the parameterizing data for my trivial module is the same as the parameterizing data for flags of ideals. And then these flags of ideals, these are the torus fixed points, they're going to give me a nice basis here. The homology. And then, let's see. Okay, so let me say, okay, that's just lining up bases. That's not telling you you have an action or why it's actually this module. And so what you have to do, you have to show now everything in the RCA acts. So for the symmetric group part, we do a very Springer-like thing, right? If you're SI, you sort of, if I is about here, you sort of say, okay, here's a two-dimensional thing. You do some push-pull, you pick the other direction. That's how SI is acting. It's a kind of standard thing. And then you say, wait, what about the X's and the Y's and the rational Cherednik algebra? How are they going to act? Well, then you say, I don't like that presentation. I want to take a different presentation of the rational Cherednik algebra. I want different generators. Okay, and so you put in slightly different generators, something that we call tau. So if you do x1 times an n cycle, and something that we called lambda, which is the reverse n cycle times y1, this along with the symmetric group will still generate everything, because once you have x1, you conjugate, you get all the other x's, right? And you have the n cycle here. So if you take these generators, you can show that they act to show that you have a representation. This guy just shifts things around. If we're acting by tau, what is it going to do? In this combinatorics, it's just going to add 1 to everything in sight. So for instance, my 12, 16, 23 will be 13, 17, 24. If you trace through what that does to this tuple, or what this does to your flag of ideals, it just says, hey, we could have put an x ik plus 1 here, and let's take the flag that, instead of starting at ik, starts at ik plus 1 and goes down here. And it's okay because our parabolic Hilbert scheme, we glued together over all k. So it's okay to go from k to k plus 1. Okay. And then now this lambda goes backwards if you can, but you might not be able to because you can't go into negative numbers, or you can't even go into 0. So you can't actually, you know this from string theory, right? You don't act on the actual geometric space. You act on the homology. And so you need to do some more clever algebraic geometry to get this to work, which ask Eugene and Jose about that. Okay. And so you can show that you have this action, and then to line them up and say it really is the representation we want, that's when you pull out these Dunkl-Opdam operators and you look at the spectrum and you see the spectrum matches. Wait, what are these operators from rational Cherednik algebra in geometric land speak? Well, you have a bunch of line bundles by, right, these guys are each codimension one in the next. And a weight that would attach to it, if we do things in sort of Z language, we could rewrite this whole picture with powers of Z's. And so powers of Z's would go, instead it would go like 0, 3, 6, 9, 4, 8, and so on like that. You'd be doing 3s and 4s, which being relatively prime, you get everything. And then you would say, oh, stepping from here to here, there was a power of Z. Stepping from here to here, there was a power of Z. Those powers of Z's, okay, they're not exactly 11, 13, and 9. You add 8 to everything, because that's m times n minus 1. So it's actually 19, 21, and 17. But you just shift your generators, they're the same. And so you match the spectrum. The representation theory, the rational Cherednik algebra is really nice with respect to when you have a nice spectrum for these Dunkl-Opdam operators. And in that way, you're like, yes, it is the representation that I wanted. And I am out of time. So thank you very much for your attention.
Any questions? Is it correct that this completely generalizes between the the Garcia Cristesi and all that stuff on the spring variety, the symmetric group acting on the spring variety? Is that like sitting inside?
Oh.
Or is it not? Or is it just analogous?
I mean, there's lots more extra going on here because this guy is like infinite dimensional. But if you restrict it, I think no. Jose is saying no. I feel like
Yeah.
oh well. I mean, again, I'm only looking at the trivial module here. Springer theory, of course, has ways of counting for every representation, and I mean, you could certainly get hooks out of this. I'd have to think about actually for every representation. These flags of ideals, they're really suited for the trivial representation. Yeah, if you want some other representation here, I don't think we know what to do.
Your other weird variety getting the L and R.
Oh yeah, that's for the Giesecke. Yeah, and there wasn't. Oh no, that you should ask Jose about that. No, that's some beautiful stuff that I don't want to say. Yeah, that just like thickens this up by like an extra CDR. And that if I drew things in terms of quivers, I could show you like what you do and you add on to the quiver. And I'm not going to try even. Yeah, I'm not going to talk about the Giesecke part, but it's great. Sorry, Jose. You can grab Jose later, and he's Giesecke man. He's Giesecke man. Yeah. Okay.
Since you mentioned Dunkl-Opdam, is there any connection to McDonald theory?
Oh yeah, absolutely. So, well, in the sense, let's see. I mean, for me, McDonald theory would really be working with the DAHA, which again, this is rational trigonometric, and then kind of elliptic is the DAHA. But yes, it does in the sense like these things do connect to symmetric functions. And if you look at stuff that Heyman does with modified Macdonald polynomials and diagonal co-invariants, and via the work of like Ian Gordon and others, these Cherednik algebra representations are models for the diagonal co-invariants. This m to the n minus 1 is a special case of n plus 1 to the n minus 1, which is the dimension for diagonal covariance. And so, yeah, these things are definitely connected. Yeah,
so you mentioned that this is like an infinite cover of some finite dimensional thing. Would that be killing the periodicity? Is that what it is?
It doesn't kill the periodicity. It just kind of normalizes things. It just says, well, it does actually, no, you could say yes, it does kill some kind of periodicity. Yeah, in some sense. You could, or rather, I want to say, so this guy here that goes 12, 16, 23, and then 24, with this being on the 0 diagonal, is different than if I started at 24. If I did 24, 28, 35, right, that's on the minus 12 diagonal, it would say those two things are the same.
Right, definitely.
Yeah, so that would smash it all down. So that's, I mean, it's still, you still need the standard condition, you still have this periodicity, but there's fewer, there's an equivalence relation on these. There's an equivalence relation on these that says these guys versus the ones that are shifted by 12 are actually the same.
Perfect. So then in that case, do you still study it by drawing this infinite tableau and then just identifying things at the end?
You could, you definitely could, although there's so many models out there using dict paths and parking functions that a lot of people use that. But this is just one more model that goes into there.
Absolutely, thank you.
Yeah, Dan.
Is there any hope to actually extend any of this to algorithms of type P?
Oh, that's a great question. So extending, yeah, where's my sticker? I'm like, what about type B? So, maybe, I mean, the thing is, there is Springer theory for other types, right? And sorry, I was looking for my stickers. So, There isn't hope for me at the moment because my Springer theory and stuff and other types is really weak. But there are, and would it actually be a Cherednik algebra or would it be some slightly different algebra? I'm not sure. I don't know if.
What you put instead of being a curve? That's the way I would avoid.
Yeah, no, that's a good question too.
So working with Oscar, given that an examining this cyclotomic case, which includes type P, okay, you need to change the geometry. It's not a Hilbert scheme anymore, but
It's not a Hilbert scheme anymore. That's right. They're I forget what you guys call them.
code scheme.
Code schemes. Yeah.
So
There's hope, especially for Oscar and Jose and other people.
Think,